This video clip is for section 1.4, Verbal and Symbolic Representations, part 2. Example 1. Make an input-output table. Let 1, 2, 3, 4 be the inputs, and the total number of squares in each figure be the output. Well, that seems pretty easy. We've got 5 squares in my first one. We've got 8 squares in my second one. What do we have here? We have 9, 10, 11 squares. And my next one, we have, what is that? That's 12, 13, 14 squares. But now, what would the fifth one be? Well, one way to look at this is that every time you go up a number, you're adding 3 more squares. We can see that from this pattern here. So the fifth one would have 17 squares. But it's a little trickier to do number 10. Number 10, you don't really want to write these all the way out to number 10. You certainly can build them with blocks if you want. But there's a variety of ways to think about number 10. Here's one way I thought about number 10. I notice that number 1 has 1 times 3 plus 2. Number 2 has 2 times 3, right there, there's 2 times 3, 2 times 3 plus 2. Number 3 has 3 times 3, right here, plus 2. So number 4 should be 4 times 3, and I think you can see that right here without me drawing it in, plus 2. Number 5 would be 5 times 3 plus 2. Does that work? Does 5 times 3 plus 2 equal 17? Yes. So I claim number 10, figure 10, would be 10 times 3 plus 2, and we get 32. So that's one way to think about this. Certainly not the only way. You might have a different way to look at that. So now I'm going to try to write a sentence that relates the input to the output. And I could say, well, the output is 3 times the input plus 2. Does that work? Well, let's think again about figure number 4. The output is 3 times the input. Well, 3 times 4 is 12, plus 2 is 14. That seems to work. So if n is a figure number, how many squares will be in the output? Well, n is the input here, so the output would be 3 times the input plus 2. And then it says if a is the total number of squares, can we write an equation? Well, a equals 3 times the input plus 2 would be a possible equation. Let's do another example, maybe a little bit more realistic. Let's say you own a restaurant and you have tables like this. Okay? So you have these tables and you have a total of 8 people around these 3 tables. So we need to find the number of chairs for other arrangements by completing the input-output table below. Well, certainly if I have one table right here, I've got 4 chairs. If I have 2 tables, what do I have? Well, I have 1, 2, 3, 4, 5, 6 there. 3 tables, well, what would happen with 3 tables? Well, if I have 3 tables, you'll notice I have 8. Do you see a pattern here? Hopefully you see that every time I add a table, I add 2 more. So 4 tables, I would have 10. How about 20 tables? Can we think of a relationship between these numbers here? Well, there's lots of relationships, but here's one way I thought about this. I noticed that 4 is 2 times 2, and 6 is 2 times 3, and 8 is 2 times 4, and 10 is 2 times 5. My input is 4, this is 2 times 5. When my input is 3, this is 2 times 4. When my input is 2, this is 2 times 3. When my input is 1, this is 2 times 2. So I think with 20, I would need 2 times 1 more than my number of tables, my input. 2 times 21, or 42. Another way some people think about this is they think, look, you need 2 on each side for each table you have, and then you need 2 at the ends. So if we have 20 tables, you'd need 2 on each side, which would give you 40, and then 2 at the ends, which would give you 42. That's another way to think about that. Using my expression for n, here would be my rule. I would have 2 times 1 more than the input. So I'm going to write that this way. Okay? So that's a little bit about some verbal and representations that we have. Now let's go back and do a little bit of, let's go look for a little bit of some review here. For this, let's convert sentences to equations. So I'd like to change these sentences to equations and define variables as needed. So why don't you pause and take a moment and see if you can do these problems. When we come back, see if you can get the same answers I did. So part A, the perimeter of a triangle, is the sum means add, the 3 sides. So I think that's what we would get there. Part B, the output is 100 divided by the sum of the input and 3. Now you have to be a little bit careful here. This is 100 divided by, now I'm going to use that as my division bar, and that's going to be the sum of the input and 3. So because it says it's divided by the sum of input and 3, I'm going to let my input be n, and then write it that way. You can also write it this way, but you have to be careful. 100 divided by n plus 3. But you've got to be careful. The order of operations would indicate that this is just dividing by n. So because I want to divide by this whole thing, I'm going to put that in parentheses. The value in dollars V of a phone card is $10 less n minutes at 5 cents per minute. So $10 less n minutes at 5 cents per minute, you could write that this way, 5 cents times n. And the product of a rational number and its reciprocal is 1. Well, here's your rational number, a over b. What does reciprocal that means? That means change the numerator and denominator, and that equals 1. Let's see if we can work the other way around by changing equations into sentences. Here I might say the output, y, is 3 more than the input divided by 2. Now, you could also say the quotient of the input and 2, or perhaps you have some other way that would be equivalent. That's certainly not the only answer. Here I might say the output, A, is the product of 1/2 B and H. That would be one way to write that. One common skill in algebra is percents. And I know all of you have seen percents at some point in your life, and it might be useful for us to just review what a percent is. So percents are useful in a number of application situations. Percents mean per 100, or divide by 100. So when we talk about 40%, that means 40 over 100, which is the same thing as saying 0.4 or 0.40. Now, converting to percents is particularly easy. All I have to do is use that definition. 55 over 100 So that's a fraction right there. Of course, that fraction could be reduced. I'll let you do that. And this is also the decimal 0.55. 7.5% will be 7.5 over 100. Now, we, in general, don't like to have a decimal inside of a fraction. So I might take 75 over 1,000. Do you see what I did there? I multiplied the top and bottom by 10, which takes that decimal and moves it over here. Of course, 75 over 1,000 can be rewritten and reduced. And again, I'll let you do that. But writing this as a decimal is 0.075. Now, you might notice a pattern here. If the decimal was right here, when I write it as percent, I'm dividing by 100, or moving the decimal 2 places to the left. So 123% is 123 over 100, which is 1.23. Now you see, I took my decimal right here, and I moved it 2 places to the left. So I claim with 0.5%, the answer is going to be 0.005. Let's see that work. 0.5 over 100. Again, we don't really like decimals and fractions, so that's multiply the top and bottom by 10 to get 5 over 1,000. So that's 10 hundred thousandths place, and you see that that rule worked of moving this just 2 places to the left. Converting to from fractions to percent notation also is pretty easy. All you really need to do is divide and multiply. So this 0.87 means 87 over 100, which is equivalent to saying 87%. 1/8, if we write that as a decimal, that's 0.125. Now, if I want to convert this to percent notation, I'm going to multiply by 100 and get 12.5%. 1.3, again, I'm going to multiply by 100 and get 130%. 2/3 is 0.66666 repeated. Now, if I multiply by 100, I get 66.66 repeated. That's a little inconvenient to write this, so typically we would round, say 66.7%. Kind of depends on what the answer wants, though. Sometimes people write this as 66 2/3%, 2/3 being this entire decimal here. 5 1/20. You need to know what 1/20 is. If you divide 1 by 20, you get 0.05, so that's 5.05. If I want to write that by a percent, I'm going to multiply by 100, so that's 505%. In algebra, we often convert sentences using percent. This example shows how to do this. Okay. So we're going to write each of these examples as a percent. So 30% of a number, well, 30% can either be written as 30 over 100, or more conveniently, 0.30, okay, is 30%. 30% of a number then would be 0.30x. Now we don't need that 0 after in the hundreds place, so we can just write 0.3x. 0.07% of a value of n. Again, I want to take this 0.7% and convert it to its decimal form. So that is going to be 0.007, and multiply that by n. And 130% of y is, let's take 130% and write that as 1.3 times y, and that ends this section.